Welcome to Module 2. In this part of the course, we shift from balances and diagrams to the practical and financial aspects of process design, equipment specification, utility requirements, and economic evaluation. Section 1: Specification and selection of process equipment. Once material and energy balances are known, the next step is to specify and select the equipment that will carry out the process. Equipment includes reactors, distillation columns, pumps, compressors, heat exchangers, dryers, and separators. Key considerations when selecting equipment are: capacity. Can the equipment handle the required flow rates? Material of construction. Is it resistant to corrosion, temperature, and pressure? Operating conditions. Will the equipment withstand process pressures and temperatures? Safety features. Does it include relief systems or fail-safes? Cost and availability. Is the equipment affordable and readily available? Specification sheets, often called data sheets, provide all critical information for procurement and installation. Section 2: Specification of process utilities. No process can operate without utilities. These are the supporting services that keep equipment running. Common utilities include water, for cooling, washing, or as a solvent. Air, for pneumatic control systems, combustion, or aeration. Electricity, to power pumps, compressors, and control systems. Steam, used widely for heating, stripping, and power generation. Accurate specification of utilities ensures that the plant can operate reliably without overloading supply systems. Poor utility design may lead to inefficiency or unexpected shutdowns. Section 3: Economic analysis in process design. Even the best technical design is meaningless if it is not economically viable. Engineers must evaluate the financial performance of a process using several methods. Capital cost estimation, the cost of building the plant, including equipment, construction, and infrastructure. Manufacturing cost estimation, the recurring cost of raw materials, labor, utilities, and maintenance. Break-even analysis, determining the production level at which revenues equal cost. Depreciation, accounting for the gradual loss of equipment value over time. Discounted cash flow analysis, evaluating future earnings in present-day terms to reflect the time value of money. Rate of return on investment, measuring profitability relative to the initial investment. Sensitivity analysis, testing how changes in raw material prices, utility cost, or product demand affect profitability. Economic analysis allows engineers and decision-makers to compare process alternatives and select the one that balances technical soundness with financial return. Section 4: Integration of technical and economic perspectives. Successful process design is not only about balances, diagrams, or equipment. It is about integrating technical feasibility with economic sustainability. A technically perfect design that cannot generate profit will not be implemented. Similarly, a highly profitable design that ignores safety or environmental regulations will be rejected. Therefore, process design is best understood as a multidisciplinary activity, requiring technical, economic, safety, and environmental perspectives. End of Module 2 summary. In this second module, we examined how to specify and select process equipment, the role and types of utilities such as water, air, electricity, and steam, economic analysis techniques including cost estimation, break-even analysis, discounted cash flows, and sensitivity analysis. These tools help engineers and decision-makers ensure that a process is not only technically feasible but also economically attractive and sustainable. To conclude, process designer has been presented in 2 modules. Module 1 introduced the foundation, the key factors influencing design, process diagrams, material and energy balances, and the use of software. Module 2 focused on equipment specification, utility requirements, and economic analysis. By the end of this course, you should now understand that process design is both a technical and an economic discipline. It requires not only accurate balances and diagrams but also careful consideration of equipment, utilities, and profitability. This knowledge sets the stage for advanced process design courses, where these concepts will be applied to full-scale industrial case studies.